Right, so today we're solving inequalities. So first of all, let's start off with a little discussion about what these symbols mean. There are a few of them actually. There's this one, which means less than. We say less than. There's this one, which means less than or equal. There's this one, which means greater than. We read them from left to right. And there's this one, which is greater than or equal. So we should start off with a little discussion about what these mean. I'll start off with the first one. Once you know one, I think it'll be easy to know all of them. If you can imagine a number line where you place the numbers that we know so far. We know 0, we know 1, we know 2. Suppose you place them in order as such. And also we know negative numbers. -1, -2, -3. And we also know rational numbers. For example, 3/2 is somewhere between 1 and 2. 5/2 is somewhere between 2 and 3, etc., etc. We actually know a lot of numbers, even like things like the square root of 5, the square root of 10 would be somewhere between 3 and 4. So these are some of the numbers that we've met in our class. There are more, but any of the numbers that can be squeezed somewhere in this number line, these are called real numbers, and we use this fancy letter here, R, to represent the real numbers. Now less than means, here's one way to understand less than. I'll give you two different ways to understand them. A cheesy way and a super powerful way to define less than. Here's the first way. The cheesy way of defining it would be something like this. Option A. Okay, here's option A. A is less than B if B is right of A on the number line. Okay, so as examples of this we could use we could say 3 is less than 4. Why? Because look at 3, it's 4 is to the right of 3, so 4 is bigger. They always open up to the bigger one, and 3 is smaller. Okay, that's one way to understand them. Another way to understand them is more powerful. This is the super professional way to understand these. A is less than B if B minus A is a positive real number. You will see that this stuff right here, this definition is incredibly more powerful. So here you can say, well, is -3 less than 1? Well, let's check. The answer is yes, since 1 minus -3 is positive. You see that? 1 minus -3 would give you 4. That's a positive number. Is 2 less than 5? Yes, since 5 minus 2 is positive. So this is an alternative way of seeing inequalities defined. The other ones work just the same way. You could, let me see here. Let's clear the screen here. Maybe go to the next one. So the other ones work the same way. So let's look at some of the other ones. We say that 5 is greater than 4 if 4 is left of 5. That would be one way to look at it. On the number line, you just figure out which one is left of who. But a more professional way would be to say that 5 is bigger than 4 if 5 minus 4 is positive. That turns out to be a much more powerful definition of a way of comparing whether or not the statement is true. Comparing the two numbers, 5 greater than 4. As an example here, 0 is greater than -10. Yes, since 0 minus -10 is positive. That makes that statement true. Right? Or maybe the baby way to understand it is just to look at the number line and see which one's left or right. Whatever's on the right is bigger than whatever's on the left. And the equal just means you have that possibility that not only is it greater than, but it's also equal. So as an example, let's do 3 is less than or equal to 4 if 3 is left or on 4 on exactly the same spot 4 on a number line. This would be definition A. Definition B, 3 is less than or equal to 4 if 4 minus 3 is positive or equal to 0. They would be 4 minus 3 would be equal to 0 if they were two numbers were equal. So as an example, 5 is less than or equal to 5 since 5 minus 5 is positive or 0. In fact, it's 0. So if you allow the possibility of equal, you get 0 on the difference. Alright, that's a little introduction to what these things mean. Now, the next task is to figure out how they play a role in our class, in our algebra class. What does this have to do with our algebra class? Well, what it has to do is that often we will have these equations that are not really equations. They behave a lot like equations, but instead of having equal in the middle, they have one of these symbols. They're called inequalities. But the goal is the same as for equations. For equations, the goal was to figure out what x is equal to. For inequalities, the goal would be to figure out which values of x fit the inequality. Alright, talk is cheap. Let's actually do one like that. So consider something maybe typical of a class like ours. A problem such as this. Suppose you've got test scores. So far you've got an 83 on a test score, a 92, and there's one more. We don't know what your score is going to be. Let's call it x. But suppose you want to obtain an average of more than 90 points. This turns out to be a classic example of an inequality. What we want here, we'll write it this way. We want the average to be greater than 90. Okay, that's what we want. Well, how do you compute average? The average would be the 83 that we already have, plus the 92 that we already have, plus the x that we're going to get. You would take this 3 scores and divide by 3, and you want that to be greater than 90. Okay, this right here is incredibly famous. This is what we call an inequality, where again the goal would be very, very similar to equations. The goal is to isolate x on one side and have no x's on the other side. Once you do that, you'll have a solution for which x's fit the criteria, and you'll know what kind of score you need to obtain an average of 90 or above. Okay, the techniques are almost the same, but they are different. Alright, so this is what we have to solve now. If this was an equation, one possibility here would be to multiply both sides by 3 to eliminate the fraction error. But that would be using the cancellation law of multiplication. And the question is whether or not we have such a law for inequalities. And the answer to that is, in fact, we do, but it's slightly modified. So we'll have to talk about that in just a second. For now, suffice it to say that multiplying by 3 turns out to be okay in this world. That's cancellation law of multiplication. Cancellation law of multiplication for inequalities. We're coming back to this in a few minutes, okay, to explain that. For right now, we're just learning the process. It's okay to multiply both sides by a positive 3, okay? If you do that, that would turn into something like this. It would turn into 83 plus 92 plus x is greater than 270. That's just by inspection, canceling the 3 and the 3 on the bottom. I could combine these. I could get 80 and 90 would be 170. 175 plus x, and that's greater than 270. That's just by addition table, an associative law of addition actually. I could subtract, here we go. Is it legal? Here's what I need to do here. 270. I need to add a negative 175 to that side, and I need to add a negative 175 to that side. And I'm wondering, is it legal to add stuff to both sides of an inequality, to add negative numbers to both sides? And the answer is yes. Cancellation law of addition for inequalities. We've got to come back and talk more about this. Why is it legal to add stuff to both sides? So put a little star on that. We're coming back to that. This turns out to be then that x is greater than that, which would become 95. This is just by inspection, and yippee-ki-yay, we've got our solution. This says that if you score 95, if you score greater than 95, your average will be greater than 90. And so you've solved the problem. What should your score be? It should be bigger than 95 so that you can get a 90. That leads to a lot of other different questions. Can we prove this? How do we know it's okay to multiply both sides by positive numbers? How do we know it's okay to add negative numbers? We've got to come back and explore these a little bit. I think these will be fun to prove. The other thing that it leads to is this idea here. When you're done solving, x is bigger than 95. There are many ways to represent this answer. Well, not that many. Maybe there's like 3 or 4. Maybe it's a good time to get to know some of these. This is one possible way to end the problem, x is greater than 95. Another alternative, I'll make a green alternative. An alternative way to do this is you make a number line and you make a indication here where your point is 95, and you open up a circle like this and you say that means that this 95 is actually not included, and then you draw an arrow and say all the x's that are bigger than that's my solution. So this would be another way to represent this, all the x's that are bigger than 95. I just drew a number line 95 and I highlighted all the x's that are bigger than 95. That would be an alternative way to represent the answer. But wait, there's more. Another possible way to represent the answer is what we call interval notation. Interval notation uses these brackets here, 95 all the way to infinity. An open bracket like this around one means don't include the endpoints. If you were including the endpoints, it would be 95 all the way to infinity, like this. The square part means that you're including it. The round part means you're not including it. Okay, that's when you have less than, greater than, or equal. That would be a place where you might include the square bracket, for example. This is called interval notation. This is the picture of the graph. This is also an acceptable way of describing the solution. Alright, that's a quick little intro to inequalities. We should come back and do a couple more, maybe take it up a notch or two, and we've got to come back and talk about this. What are you allowed to do and not do for inequalities that you were allowed to do for equations? Alright, let's come back and do more. So here's another very silly example to demonstrate how these inequalities may come up in a typical algebra class. So suppose you find yourself in an island with a 10-inch diameter pizza. Suppose you plan on being stuck there for a long time, for 21 days. So this question is asking how many should you limit yourself to each day so that the pizza will last you 21 days. So here's a visual. You got a pizza here. You're going to cut it up into little square inches, tiny little square inches, and you're asking how many should you eat every day so that it will last you. We can turn this into an inequality. The inequality might go something like this. You should eat less than there's available, less than or equal to. This time I'll use less than or equal. You should eat less than or equal, the amount of pizza that you eat should be less than or equal to the amount of pizza that's available. So how much are you going to eat? Well, you're going to eat X amount every day, and you're going to do that 21 days. For the next 21 days you plan on being stuck in an island. So that's how much you're going to eat, X square inches times 21 days. How much is available? Well, it would be the area of the pizza. The area of the pizza would tell you how many little square inches are available. And this is how many you're going to eat total. So you could say this X times 21 is less than or equal to, the area of the pizza would be, of course everybody knows it's pi r square. So X times 21 is less than or equal to pi. R is the radius, so the whole thing is 10. The radius is 5, so it would be 5 square. And so you can approximate that using some sort of calculator or whatnot. At this point it's just approximate, by the way, it's no longer equal. This would be about 78.5398. Just doing that in my head real quickly. This is how many square inches you have available, and you got to spread that over 21 days. So the amount that here's another idea. I could multiply both sides by 1 over 21. I slap that on both sides. 1 over 21 on both sides. Is illegal. Well, cancellation law of multiplication would have done it if this was an equation, but it's not, and it turns out to be okay for inequalities. Again, more to come on that. And so this becomes, back to green, x is less than or equal to 78.539 divided by 21, which turns out to be approximately 3.74 square inches. And so the amount that you should eat every single day of a 10-inch pizza, if you plan on being stuck in the island for 21 days, so that you have eaten less than what's available, should be the amount of little squares that you should eat every day should be less than 3.74. So about 3 3/4 of another piece is what you would get. You could have one piece, you could have another piece, you could have another piece, that's 3, and you could have almost 3/4 of another piece. This is how much you could eat every single day, and you will have eaten and still have a little bit left on the 21st day. Right? Okay, that was fun. That's it. I think enough little silly examples. Maybe what we do next is just practice just this part right here where we get the inequalities without the story. And also the other thing that's left to do is talk about these cancellation law of multiplications for inequalities, because that story is not complete yet. So to solve this one, you could let me see. You could slap you could say, let's go with yellow. So we have 3x is less than 10. I'm going to slap a 1/3 on both sides. Is it legal? Maybe, maybe not. Cancellation law of multiplication says it's legal to do that. Again, we got to come back and do this. This becomes x is less than 10 over 3. By inspection, and there you go. You've solved the inequality. Again, this is an acceptable answer. Often you want the picture. So you draw 10 over 3 somewhere on the number line, and you draw an open circle here, and you highlight the x's that are less than it. That would be another acceptable way of representing the solution. Yet another way would be write 10 over 3 all the way to negative infinity. This would also be acceptable. This is called interval notation. Fun, right? Alright, let's try maybe another one, a different example. What about that one? This one has greater than or equal. So, that's your given. Let's see what we can do with this one. We can use almost the same strategies that we had for linear equations. That was free the x's, move them all to one side, collect the x's, and kill the coefficient. Those things still apply here. So this would be 3x plus 3 greater than or equal to 27 minus 5x. That's the L distributive law. That's freeing the x's. Now move them all to one side. So I could add a 5x to both sides, add a 5x to both sides. Cancellation law of addition says that, but this is for inequalities. That would clean up into 8x plus 3 is greater than 27. I gotta move all the x's to one side, and things that don't have an x, they gotta go to the other side. So this 3 doesn't have an x. So we need to add a killer on both sides. So that would be, let's do it in red. No, let's do it in blue now. That would be cancellation law of addition for inequalities. I'm adding a negative 3 to that side, adding a negative 3 to that side. Again, we got to come back and talk more about these. That turns into 8x is greater than or equal to 24 by inspection. And now we can just kill the coefficient here. Maybe slap a 1 over 8 on that side and a 1 over 8 on that side. And the cancellation law of multiplication for inequalities justifies that. Again, we got to come back and talk about this one. That would give you that x is greater than or equal to 3. That's by inspection. Perfectly acceptable form of the solution. Or you can go like this. 3 x's that are bigger than 3. Fill it in. This one gets filled because it's greater than or equal to. And you shade everything that's bigger than or equal to it. That would be a perfectly acceptable way of representing the solution. Yet another way would be from 3 to infinity with a square bracket here indicating that the value is also included. That would be another acceptable way of representing the solution. So there you go. Nice little example. We'll do maybe one or two more, but really important, we got to come back and talk about these cancellation laws. They're just a little bit different for inequalities than they are for equations, and we can't leave that undiscussed.